So, Brian, go for it. Share your screen.
All right. Let's see.
Yes, and remind to mute if you aren't already.
Okay. Yep. Can you hear me and can you see the screen?
Yes.
Okay. Let's see. Oh. All right. So, as Ankur mentioned, I was going to look at or talk this morning about using spatial eddy covariance on the CHEESEHEAD dataset to investigate energy balance closure. So for those not very familiar with the project, several of the objectives here were to determine how spatial heterogeneity in the land surface impacts the Earth's energy balance, and to specifically evaluate the hypothesis that mesoscale eddies are an important cause of energy balance non-closure. So the measurement campaign took place from June to October last summer in a 10 by 10 kilometer domain in northern Wisconsin. It was a heterogeneous forest, and it was centered on a tall tower. It was a Meriflux U.S. Park Falls Tower, which has been taking flux measurements for the last 25 years. But as part of the project, an additional 19 eddy covariance towers were placed above the canopy, spread out across the domain. So, and in addition to that, there was ground-based remote sensing, airborne eddy covariance, and vegetation sampling. So the problem I'm looking at today, or going to present today, is the problem of energy balance non-closure, which just refers to the fact that in traditional eddy covariance, it's typical to measure greater incoming energy in the form of net radiation than outgoing energy, sensible and latent heat fluxes, even though they're expected to balance. So for this project, this is a plot showing the energy balance components, the mean diurnal cycle for all the towers in the CHEESEHEAD domain over the entire study period. And we see, like is typical there, that the energy balance varies across time. So we get the largest imbalances during the daytime. So on this plot, it's in UTC, so solar noon is around 1700. And you can see there's a lot of incoming net radiation. And then there's outgoing sensible and latent heat fluxes. They're the yellow and the red. The sensible and latent heat fluxes don't add up to the same amount as the incoming energy. So we see that there's this net residual that peaks midday at around 140 watts per meter squared. And that's the cyan. It goes negative during the nighttime, but overall there's an imbalance. So your daily average, there's still an imbalance. And a possible explanation for this is that landscape variance creates stationary eddies, and that the stationary eddies, their influence on the flux is not well captured by a traditional eddy covariance method. So kind of just as background, a traditional eddy covariance is a temporal eddy covariance. So how we would calculate the flux is it's the mean air density times the covariance between fluctuations in vertical wind and fluctuations in a flux quantity, like temperature, averaged over some period of time, often a half an hour. And so the key thing here for this talk anyway is how we get the fluctuation component for those. So in this traditional temporal eddy covariance method, you get the fluctuation component by taking the instantaneous 20 hertz values and subtracting the time average, so the average vertical wind speed, let's say over 30 minutes. So that's kind of your standard method. But for this project, because we had 19 plus 1 eddy covariance towers, we can calculate the fluxes a different way. We can use a spatial eddy covariance method. And in that, the difference is that we calculate the fluctuations by taking the instantaneous values and we subtract the spatial mean instead of a temporal mean. So you take the 20 hertz values and you subtract the mean across all the towers. And then there's a third method that I'll also be showing here is the spatiotemporal method. And in that's a combination of the two. So you would take, to get the fluctuations, you would take the instantaneous values, so the 20 hertz values, and you would subtract the space-time mean, or the average over all 20 towers over the entire 30-minute period. So the question here is, how do the different eddy covariance methods impact the energy fluxes? So these are plots of latent heat flux on the top and sensible heat flux on the bottom, just the daytime values. And so these are the mean daytime curves for the temporal, spatial, and spatiotemporal methods. So the temporal is in yellow, spatial is in red, and the spatiotemporal is in blue. And so what we found here is that if the spatial eddy covariance method increases the fluxes, both energy fluxes, on average a little bit, just slightly, and then we see a slightly greater increase in the energy fluxes if we use the spatiotemporal method. So combined with the spatiotemporal method, they combine to be an extra 40 watts per meter squared over kind of your traditional eddy covariance methods. So then how do those energy fluxes impact the energy balance closure? Earlier on, I showed the plot of energy balance closure peaking at 140 watts per meter squared. So that's here in yellow. That's your traditional one. And then, but if we use the spatial, we see that that peaks at about 120 watts per meter squared. And the spatiotemporal one peaks at under 100 watts per meter squared. And integrating those over the entire daytime period, we found that the spatial eddy covariance method reduced the energy balance residual by 7%, and the spatiotemporal method reduced the energy balance residual by 25%. And I didn't show the night times because there was no change in the nighttime residual. So for the sake of time, I kind of had to gloss over some of the details and some of the caveats, but I think what we can kind of say here at least is that these methods, the spatial method and the spatiotemporal method, they show potential for accounting for some of the missing energy in the energy balance equation. And so what we're going to have to do moving forward here is figure out kind of what mechanisms are actually causing the spatial and spatiotemporal EC to increase the energy fluxes overall. So possibly look at the flux co-spectra and other types of things to kind of try and actually pinpoint where they're coming in. And then the other side of it will be to take the LiDAR data that was collected and actually identify mesoscale eddies and see if we can figure out if there's a direct relationship between them and the energy fluxes that we're measuring across the domain. So with that, I guess I came in a bit early. It was great. So if anybody has any questions, be happy to take now, or you could email me later.
Okay, thank you, Brian. We have 2 minutes for questions. There's one on the poll EV, which I'll read, and just to let people know, sometimes to see the new questions, you need to refresh that page. The question was, have you considered the spatial extent of the average and the time extent of the average?
As of right now, no, we've just done the 30 minutes, and that's a good point. So for the temporal eddy covariance, we would expect probably some differences if we extended the time, possibly get some of the influence of larger scale motions. But yeah, as of right now, it's just been as is. And with the spatial extent, we don't have much ability to change that because we just have the 20 towers. So it is going to be what it's going to be.
Okay. And then another question here, was the diurnal slide 1 day or an average?
That was the average over the entire study period.